1929, Germany. An aircraft emerges from a hangar that looks more like something from science fiction than reality. Its wings don't just lift the fuselage, they are the aircraft. Passengers don't sit behind the cockpit, they sit inside the wings themselves, staring out through curved glass at the ground rushing below. This is the Junkers G.38, the largest land plane in the world, an engineering experiment that became a commercial airliner, and a vision of aviation's future that never quite arrived. Before we begin, if you're into aviation history like this, hit that subscribe button and turn on notifications. It keeps this channel going. And after you've watched, drop a comment below. Let me know, would you have flown in the wings of this thing? Now let's go back to where this idea started. When the Junkers G.38 lifted into the air in 1929, it looked unlike almost anything flying at the time. Its shape was not decorative. It represented a long-standing argument about how large aircraft should be built. During the interwar years, some engineers believed the wing itself should become the aircraft's primary volume, carrying structure, fuel, and even passengers. The G.38 was one of the few attempts to test that belief at full scale, and one of the very few to reach operational service. For Hugo Junkers, this idea was not sudden inspiration. 2 decades earlier, he had already outlined a thick, hollow wing capable of acting as both lifting surface and internal space. In 1909, most aircraft followed a simple formula: light frames, fabric coverings, and minimal structural depth. They flew, but they left little room for growth. Early aviation relied heavily on thin wings supported by external bracing. Wires and struts provided strength, but they added drag and complexity. Junkers rejected this compromise. He argued that a deep, internally reinforced wing built from metal could carry loads efficiently while improving aerodynamic cleanliness. Thickness, in his view, was not a liability. It was the solution. The First World War offered a partial proving ground. Junkers introduced all-metal wings with internal structure, eliminating the need for external bracing. These designs demonstrated the concept, but military requirements constrained size, role, and layout. The aircraft could not become what he ultimately envisioned. After the war, the technical barriers were lower. Experience had been gained. Factories existed. But politics replaced engineering as the primary limitation. The Treaty of Versailles sharply restricted Germany's ability to develop large aircraft, particularly those with long range or transport potential. Despite this, Junkers pushed forward. In 1920, work began on the Junkers JG-1, a 4-engine all-metal transport intended to demonstrate what a large cantilever wing could achieve. By 1921, substantial sections had been built, including the outer wing and rear fuselage. Then Allied inspectors arrived. They ordered the work halted, the airframe destroyed. The project ended abruptly, but the setback did not end the concept. Throughout the 1920s, Junkers continued refining ideas on paper, adjusting scale, structure, and purpose. Only near the decade's end did conditions allow another serious attempt. This time he worked closely with Ernst Zendel, translating long-held theory into a practical design path. In 1927, that effort took form as Project G.40. Officially, it was conceived as a transatlantic postal seaplane. In reality, it became a stepping stone, technically and structurally, towards something far larger. With the seaplane concept still under discussion, Junkers moved in parallel on a land-based alternative. This aircraft became the Junkers G.38. The German Navy showed greater interest in water operations, but Junkers himself favored the land plane. From his perspective, a wheeled aircraft offered broader commercial and operational flexibility. That argument proved persuasive enough to secure government backing for construction. From initial design to a completed prototype, the process took just over 2 years. In November 1929, the first aircraft, registered as D-2000, emerged from the Dessau factory. Days later, on November 6th, it left the ground for the first time. At that moment, it became the largest land plane ever to fly. Scale defined the aircraft immediately. The wing dominated everything around it. With a span of 44 meters, it exceeded many contemporary bombers and even surpassed later heavy aircraft in width. This was not a lightweight structure. The wing was built from a framework of tubular members and internal struts, bolted together and tied directly into the fuselage, forming a single load-bearing system rather than an attached lifting surface. Practical considerations shaped how that wing was built. To simplify manufacture, transport, and long-term servicing, the structure was divided into 5 major sections: a central core, 2 intermediate panels, and 2 outer panels. Over this framework, Junkers applied corrugated duralumin skinning, a familiar feature of German metal aircraft of the era. The metal did more than protect the structure. It also resisted twisting forces, helping the wing maintain rigidity under load. Thickness was just as important as span. At the root, where wing met fuselage, the structure stood nearly 2 meters tall, over 6 feet. This depth was intentional. The wing was engineered as usable internal volume, not empty airfoil. It carried systems, equipment, and people. Near the center line, directly accessible from the fuselage, the wing housed enclosed passenger compartments. Curved windows wrapped the leading edge, offering unobstructed views forward and downward. It was an unusual experience for travelers, placing them ahead of the aircraft's center of gravity and far from the conventional cabin layout of the time. Imagine sitting inside the wing of a flying machine, watching the earth tilt and turn beneath you. Moving outward, the intermediate wing sections served a different role. These panels supported the engine installations, with power plants mounted along the forward portion of each section. The G.38 used a mixed engine arrangement: 2 Junkers L55 engines paired with 2 Junkers L8 units. The larger engines were placed closer to the fuselage, the smaller farther outboard. This asymmetric layout was a compromise between power, weight, and structural loading. The higher output engines drove 4-bladed propellers, while the smaller engines turned 2-blade units. Together they produced just under 2,000 horsepower. That output allowed a maximum speed of roughly 225 kilometers per hour, about 140 miles per hour, and a cruising speed closer to 180. Performance was modest by later standards, but the objective here was not speed. It was proof that an aircraft of unprecedented size could be built, flown, and controlled using a radically different structural philosophy. The internal layout pushed the concept of an inhabited wing further than any earlier transport aircraft. The engine installations were not isolated sealed compartments. They were treated more like a marine engine room, designed to be reached, observed, and worked on while the aircraft was in flight. A maintenance corridor ran aft of the wing's forward passenger cabins. From this narrow passage, mechanics could reach the engines during operation. Routine checks, adjustments, and inspections were possible without landing. Very few aircraft of the era, and almost none since, were designed with this level of in-flight accessibility. That same corridor extended outward through the wing structure. With careful movement and limited clearance, engineers could crawl nearly to the wingtips. This access turned the wing into a serviceable system rather than a sealed component. It reflected Junkers' belief that large aircraft should be maintained continuously, not only on the ground. Behind the forward wing spaces, and separated by heavy fireproof bulkheads, were the primary fuel compartments. Fuel storage was arranged in 2 parallel rows of tanks, divided by a central walkway. This allowed direct inspection of the tanks and plumbing while airborne, reducing reliance on indirect instrumentation alone. Further inward, protected again by double firewalls, were internal storage compartments. These spaces held baggage and operational cargo and were accessed directly from the fuselage. A separate cargo hold remained beneath the fuselage, following conventional airliner practice. However, because so much volume was available inside the thick wing, this lower hold could be smaller than usual, freeing space for passengers and crew. The fuselage followed the same structural philosophy as the wing. Tubular frames and girders formed the skeleton, covered by an all-metal skin. There was no reliance on fabric or external bracing. Strength, durability, and internal volume were prioritized over lightness. The flight crew occupied an elevated cockpit positioned above the nose. This gave the pilot and co-pilot clear forward visibility and a commanding view of the aircraft's path. Below and slightly ahead of them sat a navigation compartment. Unusually, this space also included 2 passenger seats at the extreme front of the aircraft, placing occupants closer to the outside world than was typical for the time. Talk about a view. Directly behind the cockpit was the chief mechanic's station. From this post, engine performance, fuel flow, and related systems could be monitored and managed. This position reinforced the idea that mechanical supervision was as central to flight safety as piloting itself. Behind the mechanical station were the crew quarters and steward facilities. Meals and drinks were prepared here, reflecting the aircraft's role as a long-distance transport rather than a short-hop airliner. A compact lavatory sat nearby, followed by additional passenger cabins farther aft. One of these was designated as a smoking cabin, a common feature of luxury travel in the period. Comfort was a deliberate goal. The passenger spaces were designed to rival the standards of contemporary airships, particularly those operated by Zeppelin, which represented the pinnacle of German commercial travel at the time. The G.38 was intended not merely to carry people, but to change expectations of what airplane travel could offer. Control surfaces reflected the same integrated thinking seen throughout the aircraft. Along the trailing edge of the wing ran full-span surfaces divided into functional sections. The inner portions acted as flaps, increasing lift during takeoff and landing. The outer portions functioned as ailerons, providing roll control. Rather than separate components, they worked together as part of a single, continuous wing system. The tail arrangement was equally pragmatic. Rather than a single large fin, it was configured in a biplane-style layout with 3 vertical rudders. This choice was driven by force, not aesthetics. A single tall rudder of the required size would have produced control loads too heavy to counter manually. By dividing the surface, drag was managed and control forces remained within human limits. Every movable surface was dynamically balanced. This reduced the risk of flutter, a serious concern on large, lightly damped structures. Flight test reports consistently described the aircraft as stable and predictable. Despite its size, it did not behave like a reluctant giant. Pilots noted that the control forces felt comparable to those of much smaller Junkers designs, including the F-13 and the G-31. That comparison carried weight. It suggested that the design philosophy scaled more successfully than many had expected. Mass, however, could not be avoided. All-metal construction, deep wings, and 4 engines came with penalties. By the standards of the early 1930s, this was a heavy aircraft. The empty weight stood at roughly 13 metric tons, about 28,600 pounds. Maximum takeoff weight reached 21 tons. Supporting this mass was a distinctive landing gear arrangement, 4 large wheels mounted in tandem pairs. The wheels were able to pivot horizontally, improving ground handling and passenger comfort during taxiing. Springs and shock absorbers absorbed uneven loads from rough airfields. The gear was fixed and enclosed in spats with damping built into the vertical structure. At different points during its career, the aerodynamic fairings were removed to reduce weight, then reinstalled for appearance and refinement. This cycle repeated more than once during the 1930s, leaving historians to puzzle over photographs that show the aircraft in subtly different configurations. Following its maiden flight, the aircraft was purchased by the German Air Ministry. The intention was commercial operation with Lufthansa. A series of test and demonstration flights followed, drawing significant public and technical attention. On November 30, 1930, test pilots Zimmermann and Schnitzinger set multiple world records. They achieved notable speed and altitude benchmarks while carrying a 5-ton payload. These flights were not publicity stunts. They were carefully planned demonstrations of structural strength and operational capability. Testing concluded with a high-profile tour around Europe. The effect was immediate. Interest in the aircraft surged, and soon afterward it was formally handed over to Lufthansa. Commercial service began on the London-Berlin route. Almost as soon as regular operations started, a fundamental problem became clear. Demand far exceeded capacity. An aircraft of this scale carrying only 13 passengers no longer made sense. The solution was comprehensive modification. All 4 engines were replaced with Junkers L.38 units. Total power increased from just under 2,000 horsepower to more than 3,000. All engines now drove 4-bladed propellers, simplifying maintenance and improving thrust. The airframe itself was altered. Passenger spaces were expanded, raising capacity to approximately 30 passengers along with their baggage. This refit was completed in the summer of 1932, after which the aircraft returned to service. At the same time, Lufthansa ordered a second example registered as D2500. This aircraft incorporated lessons learned from the first from the very beginning. It featured a full two-deck fuselage and enlarged wing cabins, increasing total capacity to 34 passengers. An additional improvement was visibility. Unlike the first aircraft, most passengers seated in the central fuselage now had clear outside views. Both aircraft entered service together and quickly became flagships of the airline. They earned a reputation for comfort rather than efficiency. Passengers could move freely during flight. Meals and service were handled by trained staff. Although capacity remained small relative to size, the experience was unmatched. The aircraft became a symbol of German civil aviation ambition. In 1933, D2500 was given a name, Marshal Hindenburg, honoring President Paul von Hindenburg. Further changes followed. In 1934, both aircraft underwent another major overhaul. Their engines were replaced with inline six-cylinder Jumo 4 units, raising total output to over 4,000 horsepower. The aircraft were redesignated G.38A and G.38E. The careers of the two machines soon diverged. The G.38A was lost in 1936 during a workshop flight at Dessau. Incorrectly connected control cables caused a crash during takeoff. The pilot survived, but the aircraft was destroyed. The G.38E continued flying commercial routes until the outbreak of the Second World War. It was then repainted in camouflage and pressed into service as a military transport. During the campaign in Greece, it operated as a long-range carrier of troops and supplies. That service ended on May 17, 1941. The aircraft was destroyed during a British bombing raid. Plans for a dedicated military version had existed earlier. Junkers explored the concept under the designation K-51. The idea never progressed to production in Germany. Elsewhere, however, the concept found new life. As early as 1928, Japan expressed interest in the design. In April 1930, Junkers licensed it to Mitsubishi and sent engineers to assist with development. The result was the Type 92 heavy bomber, also known as the Mitsubishi Ki-20. 6 examples were built between 1933 and 1935. They were powered by 4 Jumo 204 engines and could carry up to 5,000 kilograms of bombs, over 11,000 pounds. Defensive armament included multiple machine guns and a 20mm dorsal cannon. At the time of their introduction, they were the largest offensive aircraft in Japanese service. Their usefulness did not last. By the early years of the Second World War, they were already obsolete and relegated to transport duties. None of the G-38s or their Japanese derivatives survive today. All were lost through accidents, combat, or deliberate destruction. Their legacy remains largely technical and symbolic, briefly revived in popular culture through The Wind Rises, where these extraordinary aircraft appear as reminders of an era when scale itself was seen as a solution. If you enjoyed this deep dive into aviation history, leave a like and drop a comment below. Would you have trusted a wing thick enough to walk through? What do you think went wrong with the blended wing concept? And if you haven't already, subscribe. There's more aviation history coming. Thanks for watching.